You ever wonder how mathematicians can be so sure about things? I mean, how they can prove something is true, not just for a few examples, but for all of them forever? Well, today, we're going to put on our detective hats and crack a case from linear algebra, specifically question 6 from an exam. But don't worry, forget the test. We're treating this as a fascinating file with 2 elegant puzzles that show us some deep truths hiding inside the rules of mathematics.
Okay, let's get into it. Here's our game plan. First, we'll lay out the 2 mysteries we need to solve. Then, we'll get to know our main suspects, 2 very special kinds of matrices. After that, we'll explore a really deep, two-way relationship in linear transformations, and we'll have to prove it from both directions. And finally, we'll step back and see why this kind of logical detective work is just so powerful.
So our case file here has 2 challenges, and both of them demand that we prove something is always true. This isn't about plugging in numbers and getting an answer. This is about building an airtight case, one that simply can't be argued with. The only tools we have are the established laws of math, the definitions and the rules, and we have to use them to find a conclusion that is absolutely undeniable.
And that really is the heart of it all, isn't it? In this little detective story of ours, the definitions are our facts, the rules are our laws, and the final proof is the closing argument we make to the jury. Our job is to put all those pieces together so perfectly that our conclusion is the only one possible. So, let's get to our first mystery.
Okay, our first case involves a couple of, let's call them mysterious characters. A pair of matrices with very specific identities. We're here to figure out what happens when they interact with each other. So let's introduce our 2 main players, a symmetric matrix, which we'll call A, and an antisymmetric matrix, B.
First up, we've got this symmetric matrix. The best way to think about this one is that it's perfectly balanced. If you were to reflect it across its main diagonal, from the top left to the bottom right, it would look exactly the same. Its transpose is just itself. That's our first big clue. Now, our other character, the antisymmetric matrix, is basically the polar opposite. When you flip this one across the diagonal, every single element becomes its negative, so its transpose is equal to negative B. This whole oppositional relationship, that's the key that's going to crack this entire case wide open. So, here's our first challenge. We have to prove that the trace of the product of A and B is always 0. Now, the trace is a pretty simple idea. It's just the sum of all the numbers on that main diagonal. Our task is to show that this sum isn't just 0 for a few examples. No, we have to prove it has to be 0 every single time. Now watch how we can just follow the evidence here. Each step is a logical move based on a rule we already know is true. We start with the trace of AB. Okay? First, we use a cool property of the trace. It doesn't change when you take the transpose. So let's do that. Next, we use the rule for transposing a product, which flips the order. Now we bring in the identities of our matrices. B transpose becomes negative B, and A transpose is just A. We can pull that negative sign right out in front. And for the final move, we use one more property of the trace. You can swap the order of multiplication inside. And that takes us right from negative trace of BA to negative trace of AB. So think about where the evidence led us. We just proved that the trace of AB is equal to the negative trace of AB. So what's the only number in the entire universe that's equal to its own negative? There's only one, 0. And just like that, with pure logic, we've cracked the case. No messy calculations needed. But hold on, our investigation's not over yet. Now that we've solved the trace mystery, a second puzzle has popped up. We need to show that the rank of the product AB is identical to the rank of BA. Now, normally, if you switch the order of matrix multiplication, you get a completely different result. But our job is to prove that for this one specific property, the rank, the order actually doesn't matter at all. And this is just a beautiful example of how a good detective reuses their evidence. We start with a fact we used in our last proof. The transpose of AB is just negative BA. Simple enough. Now, we just bring in 2 facts about rank. First, taking the transpose of a matrix never, ever changes its rank. And second, multiplying a matrix by -1 also never changes its rank. So if you follow that chain, the rank of AB has to be the same as the rank of its transpose, which we know is negative BA. And the rank of negative BA is the same as the rank of BA. The logical chain is complete. The second puzzle is solved. All right, let's move into our second act. This case is going to be our most challenging one yet. This one goes a little deeper into the very structure of how spaces can be transformed. We're going to investigate what's called an if and only if statement. And that's a really powerful claim of a perfectly symmetrical relationship. This is the beast we have to tame. An if and only if proof is basically a two-way street. It's like saying, this is true if and only if that is true. It means the two statements are inseparable. If you have one, you absolutely have to have the other, and vice versa. It's a two-for-one deal, which means our investigation has to work in both directions.
So first, let's get our terms straight. The kernel. Think of it as everything that gets completely squashed or nullified by a transformation. Imagine a machine, T, that processes vectors. The kernel is the collection of all the vectors you can feed into that machine that get crushed all the way down to zero. They're kind of like the transformation's blind spots. The image is the total flip side of that. It's the entire universe of possible outputs. If you could run every single vector in your space through that machine T, the collection of all the results you could possibly get, that's the image. It's everything the transformation is capable of creating. Okay, let's tackle the first part of our investigation. The first thing we have to do is assume that one side of our statement is true, that the things crushed by one pass of our machine are the exact same things crushed by two passes. Then we have to show that this assumption forces the other side to be true. So this is our key piece of evidence for this half of the proof. For right now, we're just going to treat this as an established fact. Let's see where it takes us. Okay, so proving that direct something really just means showing the image and the kernel have no overlap, except for the zero vector. So let's just grab any random vector v from that overlap. Since it's in the image, we know it's the output of some other vector u. And since it's in the kernel, we know that when we apply t to v, it gets crushed to zero. Let's put those together. That means applying t twice to u gives us 0, which means u is in the kernel of t squared. Now, we use our key piece of evidence. Since the kernels are the same, u must also be in the kernel of t. And that means t of u is 0. But wait a second. T of u is our vector v, so v has to be the 0 vector. The only thing in that overlap is 0. Done. Now for the final twist. We're going to flip the script completely. We now get to assume the other side is true, that the image and the kernel are totally separate and only overlap at 0. Our job now is to prove that this forces the kernels of t and t squared to be exactly the same. This is our new and final piece of evidence. We're assuming the entire space is built from this clean split between the image and the kernel. Let's use this to solve the case once and for all. So, let's pick any vector v that gets crushed by t squared. That means t of v equals 0. Now, let's look really closely at that vector in the middle, t of v. The equation tells us that t of v gets crushed by t, right? So it's in the kernel, but just by its very definition as an output, tv has to also be in the image. So t of v is in both, it's in the overlap. And our key evidence for this round says that overlap contains only the 0 vector. So tv must be 0. And if t of v is 0, well, that means our original vector v is in the kernel of t. We've just proven that anybody in the bigger kernel is also in the smaller one, which means they are exactly the same. Case closed. So, what's the big takeaway here? After solving these cases from question 6, what have we really learned from this little journey into the world of pure logic? The crucial point is that this is so much more than just an abstract game. It's a masterclass in how to reason. We started with simple definitions, our basic facts, and we built an absolutely unbreakable chain of logic to prove something that was complex and actually pretty beautiful. This is the exact same kind of thinking that lets a programmer prove their code is secure, or an engineer design a bridge that won't fall down, or a physicist uncover the fundamental laws of our universe. And this really leaves us with one final thought. We solved these puzzles just by methodically following the rules. It really makes you wonder, right? What other hidden truths, what other seemingly impossible problems in math or maybe even in our own lives are just sitting there waiting to be proven by the simple, elegant power of a well-constructed argument?